Radio for the masses.
Headline edition, July 8, 1947. The Army Air Forces has announced that a flying disc has been found and is now in the possession of the Army.
If the game is rigged, change the game. Game changer.
I occasionally think how quickly our differences worldwide would vanish if we were facing an alien threat from outside this world.
This is Fade to Black with your host, Jimmy Church, on the Game Changer Radio Network.
All right. Good evening, Fade to Black. Today is Tuesday, June 10th, 2025. Let's do this, man. Yeah, I'm your host, Jimmy Church. And here we go. Short week this week on Fade to Black. That's right. Last night we had James Shubsky with us, an amazing conversation about Bigfoot, the paranormal, UFOs, and portals up in the Pacific Northwest. And tonight, Marc D'Antonio is back with us. We're going to be talking about his new book, The Populated Universe, and everything else that is in Marc's world tonight. Tomorrow night and Thursday, we are off air. As a matter of fact, we are off air for the rest of the month. This will be my last show until July. Everybody relax. I'm going to live stream. I'm going to hang out on social and post pictures and do all of that. It's all because I've got TV production this week that takes me through the weekend. I get back and then just turn around, change out the clothes in my suitcase, and head south to Peru with Brian Forrester for the Inca celebration of the sun, the winter solstice. We're doing that this month, and I'm also going to go to Bolivia as well. And then I will be back at the end of June, just in time to kick off new shows on Fade to Black right here in July. And then I head out to the East Coast for the Sci Games. That is August 1st through the 3rd, 2025. And that is in Charlottesville, Virginia. And the links for that are below. All right. So let's get to it. I'm very excited. Marc D'Antonio is back with us. And we're going to be discussing his new book. It is called The Populated Universe. We're going to do that and much more. Marc, of course, he is an astronomer. He has a degree in astronomy. He is the Mutual UFO Network's, otherwise known as MUFON, chief photo video analyst. He is the host of SkyTour Radio. That's right. He thinks he's a radio host now. So he's going to come on here and show me what is up. You know what? That's really great because I get to turn this around. And maybe he will ask me some questions tonight. He's also got the SkyTour LiveStream, and you need to check that out. We've got the links for that are below. It is also called the STLS, and it is a group of live deep sky telescope observatories around the United States that broadcast live on YouTube. And the last time Marc was on the show, if you remember, he had an amazing video that he presented with us. And I think the title of the video, when he sent it to me, Something Strange. I think that's what he called it. And there you go. Always excited when he comes on. And I was with Marc last weekend at Contact in the Desert, and always great to see him. But when I speak about him to a group of people, we just need to realize the importance of his work with video and photo analysis that he has done for our community over the years. Very proud to call him friend. And here he is, Marc D'Antonio. Marc, good evening, young man. How you doing?
Jimmy, it's so good to be here. How you doing, brother?
Man, you're just a bright ray of sunshine. I was just telling everybody in the chat that you and I were talking guitars before the show, and then this explosion happened.
I heard that.
Yeah, it was crazy. And I'm sitting, I thought it came from Marc's side, and it wasn't.
I heard it through my headphones.
Yeah, it was crazy. And so I was like, Marc, I'll be right back. I didn't know if I was going to go outside and see a crater, some meteor, some asteroid, but that was loud. And we have sonic booms out here every day, and that's got a certain characteristic to it and usually shakes the house a little bit. This was more explosion-ish.
Yeah, that's what you said. I heard a dull.
Yeah, right.
I thought it was your side. I thought something fell on the floor upstairs or something in your house or whatever. But
For me, if I take off my headphones and I go, Mark, I'm going to be right back.
yeah, that worried me. I wasn't
Yeah,
sure.
it worried me, man. It was loud. And then I
sure
went
what you were-
outside, I heard birds chirping. I was like, what the heck? No smoke. I don't know what I was, years ago. I'll tell you a funny story, and then we'll move on because you're my guest, and this show is about you. It's not about
It's your
me,
show, brother. It's your show.
but no, you're a big time radio host now. So years ago, there's a road in the valley here. It's called Latuna Canyon. And Latuna Canyon goes over the mountains, the San Gabriel Mountains, and down into the valley, into Van Nuys, right? And it's a winding road, of which there's a lot of roads like that: Topanga Canyon, Coldwater Canyon, and Laurel Canyon, Latuna Canyon. So on that road at night, it's almost 10:30. There's a reason why I know exactly what time it is, but rolling down, taking these, and when you come over the hill, you just look at the valley with the lights, and it's beautiful. We've all seen pictures of it. It's great. It's amazing. And right at that moment, Rita is sitting next to me in the car. We had the sunroof open, and she's sitting next to me, and she looks up. She goes, "What is that?" And I see her looking up out of the sunroof, but I'm on a windy canyon road. I can't take my eyes off of what I'm doing. But so I'm looking, and as she says that, I see where she's looking. Right through the middle of the windshield comes this white ball, and it comes straight down, streaks, and lands in Van Nuys. Now, when this happened, I expected it didn't happen. It just landed like by the courthouse. And I called MUFON, right? I called Wolf McCarran, Wolf. I called Wolf. I'm like, dude, he's the technical director of LA MUFON at the time. Dude, oh my God. And I looked, I said, 1024 object in Van Nuys. Any reports? He goes, no, I got nothing. I said, well, keep your eye on it. We went home, Mark, and turned on the news expecting coverage. It was in downtown Van Nuys in the valley. Nothing.
Wow.
It was crazy. I still can't explain that one away. I saw it. I expected an explosion, but nothing. About a week later, we had a friend, just in passing in conversation, that said, "Hey man, did anybody see that meteor the other night? It came down into Van Nuys, and we drove down off the hill to go and find it, but we couldn't find it." And we saw that too. So that was weird. So that meant that, other people saw it, but nothing on the news.
Wow. Yeah, it's funny because I've seen some strange things, usually in our all sky camera at the observatory, and like I had something fly over, and that might be the source of the video I sent you. Okay. Because I remember something going over like this, went straight across the sky, then went like that. Now, airplanes do that, yes. But when planes turn, they tend to make a gentle curve. This one, however, didn't display any of the FAA mandated lighting that we expect. Flashing strobes at the wingtips, red and green on one side and the other. Recognition lights, maybe belly strobe that goes red every once a second. Okay. None of that was present. It was just a small, bright line moving across the sky and then changing direction suddenly. Went just like this, and then boom. And that's, I think, what I sent you. What
did you call that video?
I said it was a strange object in the sky.
I've got it. I've got it right here. Okay,
well,
I'm going to play play the video. Let me see.
I put together this little video just to showcase it.
Let's see here. I actually have it right here. Believe it or not.
I do believe it. It's Jimmy Church, guys.
Yeah,
he's got everything.
No, it's Marc D'Antonio. Okay, so here it is.
All right. Yeah, that's our time lapse.
And there it goes.
Look at that. I'll play it back. I do it slowly.
Yeah, you do. And it takes a weird turn.
It does. Look at this. Watch this.
That's pretty bizarre. And while that's the end of the video. What in this view of the night sky, what kind of distance is that, horizon to horizon?
Almost on east-west it is. If you look at the east is on the, the near side here, and the west is on the other side. And it went from the west toward the east, and as it was going from west toward the east, it changed direction abruptly. It's not an aircraft. When you take this apart and look at it frame by frame, which I have, you can clearly see that there's no FAA lighting on this aircraft whatsoever, whatever it is. And because of its brightness, my first thought was that perhaps we were looking at a rocket launch. But when a rocket launches, it doesn't abruptly change course like that. Not that I have seen.
Is there any chance that this could be like an insect or a bug?
Nope, not in this case. And this is nighttime, first of all, and it would have to be a self-illuminated bug. The only kind you get are fireflies. And if you notice, the exposures on this, there you can see them up in the upper left there. The exposures are 15 seconds per frame. And lightning bugs don't stay lit for 15 seconds. They stay lit for about a second and a half each time they flash. So this would be a bunch of, dashes on the screen at the very least. And lightning bugs don't occur out in the Sonoran Desert where this was done.
All good points. Now, let me ask you this. In real time, how long does this last?
Well, if you look at the time stamp up there in the upper left, it takes approximately, if I recall, I did the math, it came out to like 4 minutes it took to cross the sky like that.
Right. 4 minutes.
Yeah. If I recall, it was like 4 minutes overall. You can actually see when it places, I'm just recalling from memory. But it looked like, if I recall, it was 4 minutes or so.
Yeah.
See,
it's a pretty incredible shot. Now, when a pretty incredible video, when you looked at this and did your analysis, what's your take? Have you developed a take on this?
Initially, the only thing I could decide from looking at this was that maybe what we're looking at on the screen was some type of rocket launch where they changed the direction of the rocket mid-flight. That's rare, exceedingly rare, because they do change the direction of a rocket on the way up a little bit. They curve it toward the east more, and it starts to follow the Earth's orbit and kind of accelerate eastward. Okay, so it's going kind of in the right direction for a rocket launch, but it's not moving in the right way for a rocket launch, because that kind of course correction would be fatal at that stage of the rocket launch. So that's something that's not planned. You don't see rockets changing their trajectory that dramatically.
Do you think it's ET?
You know what? I sent it to you because I thought of it as a candidate for ET.
Candidate. Fair enough, man. Fair enough.
Right?
It's a great video.
Candidate, Jimmy, a candidate.
I've watched it so many times. And I keep it on my desktop. I watch it quite often. It's a pretty incredible video. Now, so let me ask you this while we're here at this stage. We're kind of jumping ahead. The book is called The Populated Universe.
Yeah.
I have stated many, 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 many times, as much as I can, to this audience about the size of the universe. Most people, you cannot wrap your head around the ginormity of it all.
True.
Okay. You can't, it's impossible, but all I can do is my job is talk numbers. Well, the other day, they released a new deep field observation of the night sky. They did 10,000 overlays, and 10,000 stitched together 10,000 images in the space of the night sky of 3 full moons next to each other. So if you look up at the full moon, right, you know how big it is, right? That dot up there, and you put 3 of those together,
a degree and a half,
right, in that one space, 800,000 galaxies.
And that's a relatively small number.
Yeah, 800. Those 3 dots of 3 full moons, 800,000 galaxies. Now, okay, that's impressive, right? That's not what's impressive about that. You move those 3 moons down, and you've got 800,000 more. You go up, you've got 800,000 more. Move it over. You can do it from any point on Earth and have 800,000 galaxies in that field of view. That's how ginormous the universe is, and people don't really get that, do they?
It goes beyond that, okay? Because that's only the ones you can see. Now, what does that mean? Okay, the farther away objects are, Edwin Hubble came up with this, back in the 20s. The farther away an object is, the faster it's moving away from us. It's moving away from us faster and faster. That's called recessional velocity. Not a problem, though. It's just a term. But understand that galaxies far away are moving so fast away from us that their light is shifted by the Doppler effect into the red. And then if you go faster and faster and faster and farther away, all their light gets shifted beyond our visible spectrum, all the way into the infrared. And that's why the James Webb Space Telescope, when it looks out in space, it's using the infrared system, the infrared light. And by looking at the infrared light of galaxies we've never seen before, it can see these galaxies that are moving away at high speed, and all of their data is shifted into the red. Now, what does that mean? It means in the same way with sound, okay, when a car goes by and it has its horn going, you hear, pew. Well, that pitch is increasing as it's coming closer, and then gets longer and deep and falls away, and pitch down the farther away it goes. With light, we don't have sound with it, okay, but we have color. When the light is coming toward us, the light turns green. When the light's going away from us, it shifts into the red. You can imagine going so fast and so far away into the red that all of that light will go beyond the visible spectrum of red, orange, yellow, green, blue, indigo, and violet, okay, and go all the way into the red. All that data goes into the red. That's where every bit of the galaxy's light resides. There are galaxies we've never seen until James Webb came along. Even the Hubble, which looks a little bit into the infrared, saw some galaxies, and it tantalized us because, wow, this means there's more galaxies even further away, moving faster. And holy cow, James Webb shows us so many more galaxies than we ever knew were there, right? And it's still not all of the universe, not by a long shot.
It's not. And then if you go beyond that and you crunch the numbers and you realize a few things that are now accepted standards, which is planet formation happens with every star. You have a dust disk, right? Planetary disk. Lumps of stuff, gravity takes over, planets are created. So every star that we see theoretically has at least one planet. We have
almost every
here.
star. Yeah,
we have 8 here, and how many small, smaller Pluto was just taken off the list.
Yeah, hang on. So, I have to just differ with this guy right now. Okay.
Yeah, I know.
Okay, Pluto is a planet to me.
It is to me too. It still rubs me the wrong way.
Let me just tell you why real quick, and then you go back to that, because you're making a really good, fascinating point. I knew Clyde Tombaugh. He's the guy that found Pluto. I sat with him on a grassy knoll. We were at an astronomy conference together, and I sat with him on this grassy knoll and talked about finding Pluto. He was a short little man, probably 4'9", okay? And he had a very small voice, and he was very, very precise when he talked. Really nice guy. And he talked about doing that blink comparator thing to see this movement of some body out there in the outer solar system. And here's the real fascinating thing about Clyde. He wasn't an astronomer. He was a worker at the observatory, but he worked there, taking care of equipment and so forth. But they gave him time on the telescope because he was a nice guy. And so he ended up finding Pluto this way. So you don't need a PhD. You don't need to be some smart guy. You just need to be someone who's passionate about looking for something. And the discoveries are out there, and there's still so many to be made.
Yeah. Well, you brought up Edwin Hubble. So in 1922, which was right here on Mount Wilson, right? Edwin's up there.
That's why I mentioned him before.
He did a lot of stuff, no doubt about it. But it was his assistant that did all the work, right? She's
of course.
The one that, looking at the plates and the photographs. And she deserves probably more credit than Edwin. But back then, it was a man's world, and it was a different. I'm talking about in astronomy. If you were a woman in astronomy, it was a bad day. But it didn't happen with both of their hard work and math. He didn't get published until 1928. Nobody wanted to accept Einstein. He had to take Einstein up on the hill, right, up on Mount Wilson, and force Einstein to look, because Einstein, until that point, said it's static.
Yeah, that's right. There was the oscillating universe, the inflationary universe, and the static universe. We didn't know. Okay, but until Edwin Hubble found that special Hubble constant, which now we find out isn't a constant after all, it's the rate of expansion. We thought it was a constant. Well, no, it's actually doing this. It's accelerating outward every second.
And we didn't even figure that out until 1998.
Right, exactly. Yeah, so that was
crazy.
So
back to let me get back to my point. So it's a numbers game.
Yeah.
If we look at what is happening, here's just a basic number. This is a Jimmy Church number. All right. How many planets are in the observable universe? The key word is observable. Well, it is, I'll just give you a rough number. It's 100 billion trillion.
Now,
that's crazy, isn't it? That's 100 billion trillion.
When Titanic sunk, that the concept of losing like 1,200, 1,500 people, they didn't know what that looked like. So in order to bring that number to reality, to make it visceral for people who are learning how Titanic sunk, to see the actual cost of loss of life, they put 1,500 people on the docks in Ireland, in Belfast, okay, and took a photograph. That's when people understood, wow, that's a lot of people who died, okay? So chapter 1 of my book is called The Problem with the Numbers. And you can see the problem with the numbers, 100 billion trillion. People are sitting there going, okay, billion, and 9. Okay, oh, wait, what? And they just, their minds go, right? So they don't get it fully. So you have to use analogies. Okay, if I tell you that the actual diameter of the universe, okay, isn't that 13.8 billion light years that we can look out and see at the edge of the universe, but it's actually 92 billion light years in diameter.
Yeah,
how?
People don't understand that. They don't understand that. They think it's 13.8, and it is not. It's almost 95 billion light years across. And okay, so let's stay on this numbers game. Let's stay on chapter 1 in the book. Just our Milky Way. Okay, so addressing Hubble. The original Hubble deep field, which is, to this day, I think it was one of the biggest turning points in human history, the original deep field. And so when they realized, because they took the darkest part, emptiest part of the night sky and exposed it for a month, and then checked out that image, which turned out everything that they thought was just a star or a pinprick of light turned out to be a galaxy. And the more that they unlocked, everything in that image was another galaxy. It was a huge turning point for us.
An island universe.
Yeah, that's right. That's right. And that was just a black spot That was the darkest, emptiest spot of the sky that they could find. Anyway, we take galaxies for granted right now. We just talk about galaxies like we talk about the number trillion. We just throw it around when we don't really understand. Our Milky Way is 150,000 light years across. Our Milky Way. And we just think it's just some little, some little thing. No, it is our Milky Way, just our Milky Way. Forget about our galactic neighborhood, but our Milky Way is giant, isn't it?
Yeah. I mean, if you think about it, this Milky Way we live in, all right, of course, we're concerned with Earth, our cars. Is our car going to start tomorrow? What's the weather going to be like? Meanwhile, leave the atmosphere behind, go out into the universe, look back at the Earth from a distance. There's no borders, there's no wars, no strife. You can't tell anything. It's just a big, beautiful blue ball. Okay. However, keep going further out. And now the solar system gets shrunk down to a little tiny dot, right? And you keep going, and now the sun and the solar neighborhood of nearby stars shrink down. And then the rest of the galaxy starts coming into view. And as you said, we have 150,000 light year diameter to our Milky Way. Now, that means that light takes 150,000 years to cross it from one side to the other. That's how big it is. Light travels so fast that it goes almost eight times around the Earth in a second, if you can make it go circular. All right? So think about that. And still, it takes 150,000 years for that very, very fast light to go across our galaxy. Then it takes 8 minutes for the light to get here from the sun. So that's how far the sun is away from us. And we still have a planet that's bathed in life-giving warmth and radiation, right? So if you look at that and say, well, is Earth really that rare? Well, maybe Earth with a moon this size might be somewhat rare, because we are kind of rare in our solar system for planets with moons that are kind of as large as the moon is, okay? However, there is the chance that in our galaxy, there's two calculations, okay? They redid the Frank Drake equation, okay, the Drake equations a number of times. An Italian group did it. A number of other groups did it. And in one case, they said, well, we're going to err on the side of conservatism. Now, we can't see the other side of the galaxy. It's all dusty. We can't see through it, okay? So we just infer what's on the other side. We're just guessing. We can't actually see it. We're in the forest. We can't see the extent of the forest. We look at the Andromeda galaxy. We see the extent of the forest. We see the whole forest of Andromeda stars, right? But in our galaxy, we don't know. So we have maybe upwards of 100 billion stars in our galaxy, and that's the low end. The high end is 400 billion, because we can't see the other side to actually do an accurate count. So at 100 billion, the number for the Drake equation is somewhat low. Earth-like planets in the habitable zone of their star, stars that can support life like us, those planets number about 25 million at that, just in our galaxy. Now, that's still a huge number. Now, if we go to 400 billion stars and we interpolate outward, guess what that number goes to? It goes up to 40 billion planets just in our galaxy alone. And by the way, our galaxy is no giant galaxy. It's a medium-sized galaxy. The Andromeda galaxy, okay, if we have 100 billion or 400 billion stars, the Andromeda galaxy, which by the way is heading right for us, okay, in a couple billion years, it's going to collide with us and merge with us and make us into a new galaxy, okay? Well, when it does that, the Andromeda galaxy has 1 trillion stars in it, okay? We have 400 billion at the high end, okay? So literally, Andromeda galaxy is more than twice the size of our galaxy. So it's twice as massive. And so I think it's more right to say that we might be speeding toward it a little faster than it's speeding toward us, okay? And like that croquet ball, okay, when it gets hit, the other ball is going to go sailing. Well, we're going to end up going around and orbiting the Andromeda galaxy until we merge with it and become this new galaxy type that we may not have seen before. Or maybe we see them all around us and don't know where they came from. So,
there was a press release this week about that, saying that it is possible that Andromeda may miss us. It may be off by a degree or two. It's still a ways off from happening, but did you see that press release and that?
Yeah, let me explain what that could imply for us. It's probably better if we were to hit directly. First of all, when we say hit, nothing's going to hit. The stars are going to go boom, they're not going to collide. That doesn't happen with galaxy mergers. There's galaxy mergers all the time. In Ursa Major, the Big Dipper constellation, there is a galaxy called the Whirlpool Galaxy. It's this beautiful spiral face-on like this, but then it has this other galaxy right here. It's trailing off this stuff. This galaxy came down and hit the Whirlpool Galaxy and went through it and bent its disk downward as it went through. So from the top, it looks like this, but from the side, we see this bend, okay, and in the bend in the main galaxy, and this galaxy is on its way through, and it's dragged out a whole bunch of the stars behind it and left this arc, okay? So in those two galaxies, there isn't chaos. It's just a redistributing of the galactic gravitational, forces, and any creatures there may not even know what's happening and probably would never have known it's happening. It might not ever have influenced life. The most it could do is bring a star that may go supernova at some time close to it and close to their planet, by a light year or two closer, and that might spell a difference between survival or not surviving if there was a supernova. Like if Betelgeuse, the upper left star in Orion, that beautiful orange star, okay, that star is supposed to go supernova sometime. It's 750 light years away. It may already have gone supernova, and the light train hasn't reached us yet with that information. And when it does, we'll see Betelgeuse get suddenly very bright. It'll be so bright that if it happens while Betelgeuse is in the daytime sky, we'll see it in the daytime sky like a second little sun in our sky for a period of a couple months or more. And then it'll fade away into obscurity. And then we'll see this gorgeous nebula start forming around Betelgeuse over time.
Yeah, the famous sighting from Chinese astronomers in 1400 was a new star in the sky that lasted about a month. And they now think that was a supernova that was witnessed in, I think it was 1423. But can you imagine back then? I think about this all the time because the night sky was their high definition TV. That was their Netflix. That was their Amazon Prime.
And there was no light pollution.
Right. And then suddenly you've got a new bright ass star in the sky. So here is, I'm just going to pop this up so everybody can see what we were talking about. This is the Hubble Deep Field. And so just imagine, they didn't know what was going to happen. This was, I think it was, I said 30 days earlier. I think it was about 2 weeks. I could have the days wrong. But anyway, this was the darkest part of the night sky. There was nothing there. And they exposed it for 2 weeks. And then this is what they got back. Everything you see here is a galaxy. And what was crazy about this, Mark, was this was black.
Yeah.
Right. This was black. And so they go and they expose, and then, as they enlarged this and enlarged it and enlarged it, every little dot that you see in this picture, every little tiny speck is a galaxy.
Yep.
The galaxies just kept coming and kept coming and kept coming. But that's the Hubble Deep Field.
Yeah. And if you look at that too, Jimmy, what you'll notice is some of these galaxies, like this one right by my finger here, okay, that orange one, okay, that one's orange because it's actually further away, moving faster. So its data is being shifted into the red end of the spectrum, like I've been telling you about. So the Hubble can reach a little bit into the infrared and see some of these galaxies whose light has been shifted into the red. So that's why some of these galaxies are red. You'll notice also the different shapes. Okay, right in the center at the top, you got that spiral galaxy with the arms, okay? Well, spiral galaxies with arms are what people think spiral galaxies look like, but they don't all look like galaxies. Okay, look at the orange one underneath the C and fade to black there. Okay, that one there is what's called an elliptical galaxy. Just next to the word live in the lower right is another one, this big giant circular thing. It looks like a star, but it's not. That's an elliptical galaxy. These are super massive galaxies that are spherical and have billions upon billions upon billions of stars, maybe trillions of stars. And
I love that spiral right in the middle.
Isn't that something? Look at that little one right below center.
Yeah, just beautiful, man.
Yeah, we take pictures just like that with our SkyTour LiveStream cameras. And we expose, we have a system that's so fast that we can expose and capture galaxies in just like 20 seconds, 30 seconds. And people get to see, not this detail, but close to it per galaxy. It's really something. And every one of the galaxies you see there, every single one of those, most likely has life that's formed somewhere within that galaxy. And that's what I talk about in the book. I mentioned.
Well, okay, let's stay on this numbers game.
Yeah.
We'll stay with let's stay with our Milky Way first, and then we'll literally spiral out. Let's spiral out.
Sure.
But it's a numbers game. So if we're talking about a minimum of 40 billion Earth-like rocky planets in our Milky Way in the Goldilocks zone, that's a huge friggin' number, but it's not that big. But it's still big. It's a lot bigger than you remember the Drake equation. They first ran. Oh, the number's probably then they changed it to 10,000. They were like, okay, 10,000 is the number. Well, we're now sitting at about 40 billion Earth-like planets in the Goldilocks zone.
Yep.
Out of those 40 billion, what's your take? How many do you think could have intelligent life?
Well, keep in mind that intelligence isn't an end game for every single life-bearing planet. It's a potential journey. It's a potential endpoint. So look at our planet, and all we can do is look at our planet and extrapolate. And I've done this many, many times. If you look at how life happened here, we exist exactly the way we do because of 5 major extinction events that occurred on our planet. All right. 252 million, I won't go through them all, but I'll just tell you the highlights. 252 million years ago, during the Permian period, the animals that ruled the world back then were the things that would possibly become mammals like us. So smaller animals that had the ability to change to mammals, okay, warm-blooded creatures like we are. But then a massive volcanic eruption in what's now the Siberian Traps, it flooded underground, and then it was under a lava dome, a lava cap that went out miles and miles and miles and miles, and then it just burst out, and gigatons, that's billions of tons of carbon dioxide, shot out. And over a period of time, a short period of time, a week or two, the temperature on the planet rose 21 degrees Celsius. That is an Earth life-shattering event. And so when you raise the temperature of seawater that has oxygen in it, from phytoplankton building oxygen, which is what was in there, when you raise the temperature of seawater, it's harder for oxygen to stay in the water. So we lost a lot of the marine life. We actually lost 96% of all life on the planet. Okay. And the creatures that would become mammals, of course, retreated into small niches of tiny bits of survivability here and there. But guess what? That extinction event paved the way for the age of the dinosaurs. And that led us all the way, millions of years, all the way to the Jurassic age that we call it the Cretaceous Tertiary boundary, where in the Cretaceous, the late Cretaceous, we had this amazing event where a asteroid struck the planet. Again, a big pall of dust goes up, and now the dinosaurs that ate plants died, and the meat eaters that ate them died. Now, it took some time, obviously, didn't just all die. Okay, so over a period of a couple months, the Earth lost 96%. And when all the dust settled, figuratively and realistically,
right,
those little creatures that were hiding in the dark, that would become mammals, reemerged and filled those empty niches that were now wide open. And that led the way to us. Right now, had that not happened, I've done this many times. I've talked about it. I have a lecture on this. I talk about this often. Had that not happened, is it possible that Jimmy Church and I would be talking, and I'd have yellow eyes and I'd have some scales? And, is it possible?
Right. Is it possible that dinosaurs would have ended up building radio telescopes?
The likelihood is not as high from our perspective that we look at it, because dinosaurs would have had to have environmental pressures to do
and opposable thumbs. You need
you need these.
You need those.
You can do with this, Okay.
Yeah.
But the dinosaurs were increasing in intelligence. Certain ones. One of them was the Troodon, And that's true, Troodon. Okay, the Troodon was actually increasing its cranial capacity quite alarmingly when it was snuffed out. So that's true of other life forms too that were, changing their evolutionary adaptability, and they also died out too. So and so those are just two of the extinction events. There are three others.
But do you think? No, let's stay on this though, because we have the reptilian side of our brains, right?
Yeah,
we talk about that. I get that. But if that cosmic event does not happen, do dinosaurs over the next 65 million years evolve into a super intelligent species? Do they what's the big, okay, all right, fire. Do dinosaurs figure out fire? Without fire, there's no technology. Octopus, very smart. Very smart. Smarter than us.
To make fire.
No fire, no cell phones for octopus.
Right. Well, you could have 8 of them, right? Hey.
Yeah. So do dinosaurs figure out fire?
If the environmental conditions would force them to innovate, then perhaps. However, they'd have to have the cranial capacity, the brain case capability to actually develop such technology, and you'd have to have a reason for it. As we know, dinosaurs would capture something, eat it raw, and that's what they did. And in all the time,
so did we.
Yes, but in time, we discovered that survivability required us, and I don't know how it happened the first time. It was probably an accident, probably a lightning strike, and someone finally ate that monkey that had been struck by lightning and said, "Hey, Torg, this is pretty good. Have a bite." Right?
Can you imagine that first day? The burnt cow, and you're
exactly.
Like, wow, man.
Hey, how did we do this?
Yeah, man, these ribs are amazing.
Torg, you're in charge of fire. Go get that fire. Go stand with that thing and grab the lightning.
Do you remember the movie? You're my age. I'm trying to think of the name of it. I think it was Quest for Fire.
Oh my gosh, yes, that was an old movie.
Yeah, with Ray Don Chong. It was like Tommy Chong's daughter. Ray Don Chong was the star. But that was the Quest for Fire. Keeping they had a little like piece of, it was like bone, right? They had this, and they had the little fire, and you couldn't let it go out.
Couldn't let it go out. That's exactly right. You're in charge of fire.
You're Quest for Fire. That was such a great movie.
Yeah.
And although that's artistic freedom today, I'm not so sure that is far off. I bet fire was that precious back then.
I would guess you're right. As a matter of fact, that's why I think there would be a common cave fire if they were in caves, and somebody would always be tasked with keeping that fire going. And if it went out, it could mean you're dead and that they eat you raw. I don't know. Okay, but still, it has that same implication, doesn't it? You got to keep the fire going. And so
doesn't in that movie, hold on. It's coming back to me. I need to watch it again. He's got the fire. He's the fire protector, but doesn't he get stuck in like quicksand? And he's holding it up and he's getting sucked down, and then the fire goes out. And so he goes on the quest for fire, and then that's when he hooks up with Ray Don Chong. She's in another tribe, and they had figured out flint.
Make
right
fire.
So his tribe, they had to keep the flame burning, right?
Mm-hmm.
He goes to the next tribe, and they're like,
make a flame. Yeah,
they were lighting it really easy, and it was faced right. So he brings her back with him back to his tribe. They're waiting in the cold, right? Yeah, I remember that was a great movie. That was a great movie.
Yeah. Jimmy, I gotta watch it again now. That was so cool. I forgot all about that.
She was like Merlin.
You got a good idea.
She was like Merlin.
Yeah.
Ooh. Yeah.
like a
It's a great
Larson
movie.
cartoon. Ooh.
Okay, so back to this idea, though. Okay, so 40 billion Earth-like planets.
Mhm.
Something is visiting us.
Yeah,
And if they're getting here, that means they are more advanced.
correct.
I would say, based on everything that you and I discussed, they had to go through the same stages of evolution, didn't they?
Exactly. Their planet would treat them very differently, most likely. I mean, Earth is not the best planet for us, to be honest. It's not what we call a super habitable world. Okay.
Have you been to Vegas? I think it's pretty cool.
Yes, I've been to Vegas a few times. Okay. And yeah, it's pretty cool. All right. But I will say that the planet itself is always trying to kill us. Okay. We have tectonic activity, which causes earthquakes, which causes tsunamis, which causes volcanoes. Okay. And people always lose their lives in earthquakes, tsunamis, tornadoes, okay, volcanic eruptions, and so forth. And of course, that never mind the stupid things people do. I mean, that stuff just goes without saying that people Darwin themselves all the time. Okay. However, if we look at our planet, I mean, we've got these thin crustal plates riding on top of a molten interior. And so we literally, at any one time, we have molten lava all the way to the Earth's molten magma all the way to the Earth's core. If you're at Yellowstone, 2 miles beneath your feet all the way to the core of the Earth. And if you're here in Connecticut, where I am now, it's around 65 miles all the way to the mantle, and then now to the heat all the way to the bottom of the Earth into the core. So it varies. The depth is different all across the world. But, you know, if you think about it, even though it's not that hospitable for us, Jimmy, we actually figured out how to handle it, how to live. But it also means that if you look at the different life forms that have occurred on our planet, we've had hundreds of millions of life forms come and go extinct over the long haul. And this is probably because our sun is not a perfect star for human habitation or life forms, because it spews enough ultraviolet energy that it can cause mutations to the DNA, right? The fabric of life on all the world, all of our world has the fabric of life as DNA, causes enough mutations to cause all these random, and they're called radiative adaptation. They all radiate outward from one common ancestor. And so all this stuff radiates out. Many of those die off, but some of them are selected to continue because they survive the conditions that they mutated into better than all the rest of these guys. So it's like an automatic process of selection. That's why it's called natural selection, right? So we've had that happen here. Maybe on a planet that was much more stable, one of the 40 billion potential planets elsewhere, they didn't go through all of these different major extinction events. Maybe they don't have asteroids that strike their planet. Maybe they have fewer. Maybe they have more. Maybe they're not here yet. Maybe they're not even at our level yet. But if you think about the ones that maybe are more stable, think about what they went through. They were able to move unfettered into their technological age. They got through their nuclear age because everybody has the same atoms in the universe.
They didn't kill each other.
They figured out how not to kill each other. Most likely they were warring. They had that conflict and they got rid of the conflict. They had to get through their nuclear era. They had to get through the wartime issues. They had to learn about fusion. They studied their star. Again, the same atoms all over the universe have the same power no matter where you go. It's just yours to find the secret of. And so that's probably what they had to do. They figured out fusion. They probably have fusion reactors. We're trying now to do them at Lawrence Livermore Laboratory. They've made a sustained reaction for the first time, a year or so ago. That's a major milestone, even though they didn't get out as much energy as they put in.
They did it last week for 43 seconds.
Yeah, incredible.
Yeah,
right?
43 seconds.
And they did it before as well. All right. And now the thing is, we're actually making these strides in fusion power. That figures prominently into where we're going when we want to go interstellar. And that's actually one of my most popular lectures. I've been giving it all over the country lately. I gave it at Contact among the other 5. And I did 5 total, 2 Skywatches and 3 lectures. And one of them was interdimensional travel. Okay. Now, if we can actually do this travel mechanism, then what we can do is we can go from one place to another without traveling through all the points between one place and the other. We can go from here to here.
How do you do it?
I'll tell you. You go from here to here, Okay. You disappear from here and you go into a fifth dimension up here. See, it's off the frame. It's meant to be because you can't see it. And then you just appear over here. So now how does that work? Well, there are certain particles that CERN at the Large Hadron Collider has been playing with and actually built a detector to detect. And it's called the Atlas detector. And if you look up CERN and Kaluza-Klein particle, you'll find the white paper. It's Kaluza Klein. And if you look that up, CERN and Kaluza-Klein, you'll find the white paper that discusses the research into Kaluza-Klein particles. And the idea is that the Kaluza-Klein particle can create a pathway to this fifth dimension. And that would mean that we could get out of our four dimensions, X, Y, Z, moving through time. Everything we do, we're at a new coordinate 10 seconds from now at a new time. Move over here, we're at a new coordinate at a new position in time. Okay. So and we travel through every spot in between. But using the Kaluza-Klein hypothesis and using these particles called Kaluza-Klein gravitons. Now, this is a short form of this talk because obviously I don't have time to develop the whole graviton concept with you, but I can say this. All the elementary forces, the strong force, the weak force, light, and gravity, those first three, strong, weak, and light, are well understood. They fit within a little box that we call the standard model. They fit really nicely. Gravity, that's the outlier. That's over here. The gravity's the outlier. We can calculate its force. We can calculate what it can do. We can put people on the moon. We can go to Mars, land rovers on Mars, go to Pluto, leave the solar system with the Voyagers, and do it really accurately because we can calculate how gravity is going to tug us along. We can't, though, reflect gravity. We can't refract it. We can't harness it. We can't utilize it. So that's what the Kaluza-Klein graviton offers us, because if you look at the classic UFO shape, right, it's a disc or a triangle, right, pretty much. And you have orbs and cigar shapes and stuff, but you have this disc shape. Why a disc? Why round? I say it's because they're particle accelerators, and they're actually dispensing particles around their periphery of these Kaluza-Klein gravitons, which they've figured out, and we're on the verge of figuring out. And those gravitons live in a fifth dimension. And have you had Michio Kaku on the show before?
I have. Let's stay here though.
I'm getting there.
So then I can understand the particles going into the fifth dimension, but how do you take the craft with you?
Because you're surrounding your craft with them. And so the craft ends up getting subsumed into it with them. This is something that is part of Bob Schroeder's book, Solving the UFO Enigma. Good buddy of mine, excellent.
Yeah, great
author.
Great book. Yep. One of the best shows I've ever done was with Bob.
Yeah. And so Bob, I joined his thought process. I went through the book. It's written for people that can understand the math. I get it, and that's fine. Yeah, you have to get it across somehow. But I've been taking that and popularizing it with his blessing, of course. And the point is that if we can get into that fifth dimension, the fifth dimension has a name. It's called the bulk, like bulk produce. But again, this is part of a string theory variant called Randall-Sundrum 1, RS1. This isn't made up stuff. This is part of a string theory variation. And so if you can get into that fifth dimension, guess what? The universe gets smaller and smaller and smaller around you as you go deeper into it. It's highly exponential. So what does that mean? It means that if you travel 12 inches out here in our four dimensions, you go 1, 2, 3, 4, 5, all the way to 12. You go 12 solid inches. Now, take and go into that fifth dimension and travel 12 inches if you go in just a little ways. That 12 inches that you travel in there, when you come out, gets expanded to some massive amount. So now that 12 inches expands, say, to 150 inches or whatever. Okay. Now travel 10 miles in there and go farther in. Well, that 10 miles could take you to the moon or to Saturn or Jupiter or maybe Pluto.
In fractions of a second.
Yeah, because you're not even in our dimensions. There's no light speed limit.
When Bob explained that to me the first time, and he made it, and you're right though, he's got a way of explaining it that is very elegant. But wow, what a concept!
Right. And now here's the thing. This is why UFOs are shaped the way they are. They have to dispense these particles. So if you're in the inside center of a UFO or disc-shaped UFO, you're safe when you put shielding around you. Okay. And the outer ring dispenses the particles. If you contact this as a human being, you walk up to a UFO and touch it, what do you hear people say happens? They get burned. Things happen, right? They oh gosh, it feels too cold or it feels hot, whatever. There's a reason for that. And that is that when you're trying to send particles that want to go straight, charged particles that want to go straight, you're trying to confine them to a curve using a magnetic field. They give off radiation called synchrotron radiation, which isn't good for us. Okay, so people exposed to these things get radiation burns and sometimes radiation sickness, and that's the thing that we see historically throughout the UFO world. So that's something. Now here's the other thing. Because they don't actually travel in a line, they travel in discrete jumps. They start here, they pop out, and they pop in here, then they pop out and pop in here. So to our instruments, it looks like they went really fast. But it looks like they can also do this. They can go bump, 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 bump. And now people say, look, that traveled in a right angle. Nothing could survive that rapid G-force. That's right. And neither can they. They're just popping in at a new coordinate from the fifth dimension. So by doing that, they just see the scenery change outside their window while they're doing this. And the other thing, if they want to hide from us, they don't have to go to the far side of the moon. Actually, we've got good coverage of the moon with the Lunar Reconnaissance Orbiter. All right, we've got the Lunar Reconnaissance Orbiter quick map. You can go on there and dig down the moon to see things the size of a large boulder everywhere on the moon almost. So we got that covered. They don't have to. They could be in the deep ocean, right? And we hear about these USOs all the time. In fact, Congress has been having them on there. And I may actually be asked to testify in Congress about the USO event I had. But these ships, if that's what they are, right, can stay forever in deep ocean because they just go back and forth between this fifth dimension and the four dimensions, and they just do it rapidly. Okay. And if I go fast enough, you can't even see my finger. If I slow it down, you can see it moving back and forth, right? Well, if I'm going too fast, high frequency, then I'm neither here nor there. So
well, you know what else that explains? The lack of bedrooms on flying saucers.
No need.
Yeah. Always the little chair. Right. And no fancy creature comforts, no pool table. Right. Yeah. You know what I mean? No artwork on the wall. They don't need. It's
not a generation ship. They don't need
it's not a generational ship. Yeah.
No, they just go about their business. And I have a theory too, that it's possible that the creatures that take people with this indifference that they sometimes show, not all of them, but some of them show indifference, are biological robots. I mean, we're doing it now. We're trying to create robots, right, that look like us. Maybe they create them in their likeness too. Not only that, maybe they invested in looking into biological memory and creating, I would say, clones, but robots that are biological in nature. And even though they may be somewhat sentient, they don't care because we can't impose our morality on them. So we don't know how they feel about this kind of stuff, right? So that's a cool thing. I don't know. I think that this is the only way that they can actually be traveling the universe. And guess what? Because of our blue marble that's seen from now, we started producing oxygen in our atmosphere 2.5 billion years ago.
That's
so
right.
We have a signal that's gone out to a great chunk of the universe, right? So if you see that you got a big blue marble over there, you know that the blue color is due to oxygen molecules scattering the blue light from the sun. That's why our sky is blue. That's why it's blue everywhere you look. Nitrogen and oxygen scattering that light. So people say, hey, Torg, that's a planet that's like, maybe we could survive there. Well, why would we survive there? Because we're carbon-based too. Carbon-based beings would need oxygen to survive. And so oxygen in an atmosphere is very promising to them. And carbon is the fourth most abundant element in the whole universe. Ooh, guess what's third? oxygen. So it's a love affair between those two elements. And carbon is amazing at making bonds and breaking bonds in a biological system like we are. As you sit there, you've made and broken probably 500,000 bonds sitting there. You get excited, you made a bunch of sugars, and it goes on.
We need to take a break. When we come back, I want to talk about Bennu. Okay, so we'll do that in just a minute. Marc D'Antonio is our guest. I'm your host, Jimmy Church. We're talking about his new book, The Populated Universe. This is Fade to Black. We'll be right back after this short break. Stay with us. Subscribe to our YouTube channel to get your alerts and access to over 2,000 videos. Click that subscribe button right now. Go to jimmychurchradio.com and get the Fade to Black official podcast. 2,000 episodes, all of them commercial free for just $2 a month. Watch Into the Vortex on Gaia TV. It's Fade to Black for the screen. Simple to do. Go to Gaia.com, search Jimmy Church, or click on the link below. Follow Fade to Black on Twitter at JChurchRadio. Get all of the show updates every single day. It's now called X, but who cares? How you doing? Jimmy Church here. Special announcement. Get your Fade to Black t-shirts. That's right. Help support the show. Help support everything that we do over here. We've got 2 t-shirts. We've got 2 ways to get them. Get your Fade to Black t-shirt today. Go Beckley Teppy. Go to jimmychurchradio.com and become a Fadernaut. Get a membership. That's right. Everything is commercial free. You have access to downloads, and you get to call yourself a Fadernaut. Today we're headed to Bolivia, Tiwanaku, Peru, and of course, Pumapunku. Brian, exciting. Thank you so much for everything, my friend.
Always an honor. Right behind us is the sacred river of the Inca that goes past Machu Picchu. So we're going to be driving up to its source at 15,000 feet above sea level and then down to Lake Titicaca.
So today we hit 15,000 feet.
Yes.
Crazy. And you can do it with us. All you have to do is go to hiddenincatours.com. Simple. We've got 2 tours coming up next year, one in June for the summer solstice, right? And then another one right here in November. So hiddenincatours.com. Come and hang out with Brian and I and his amazing team.
Right on.
River Moon Coffee, makers of the Fade to Black blend. Truly the best coffee on planet Earth. Just visit rivermoonwellness.com or their Amazon store. It's all simple to do. You can check out the Fade to Black blend, the Game Changer blend, or any of their Black Moon Wellness products. It's the only coffee I drink. It is the best, and it's Doc. Again, rivermoonwellness.com. All right. Welcome back. Fade to Black. I am your host, Jimmy Church. Tonight, Marc D'Antonio is with us. We're talking about his new book. It is called The Populated Universe. The links for Marc are below on our website and throughout social media. Let's get back to it. Mark, the samples from asteroid Bennu came back, landed in the desert of Utah, and the samples were collected. And it turns out that they found the 20 basic sugars that amino acids that make up RNA. And in addition to that, which is the precursor and the instruction set for DNA, they found the 5 proteins that make up DNA on a random asteroid out there in the vacuum of space. Now that says a lot to me. What did that discovery mean to you?
Here's what that meant to me. Okay, first of all, in the book, I point this out too. As I say, carbon's the 4th most abundant element in the universe, so it stands to reason that there's going to be asteroids that are carbon rich, and Bennu is a carbon rich asteroid, and it's full of organic compounds too. Organic means there's a lot of carbon, right? And so these compounds in the asteroid in the past have made their way to the Earth through other impact from other asteroids. And this is something that people generally don't understand. They don't generally think about it, but we've had many impacts on our planet from asteroids in the past. Now, the Earth itself makes a lot of compounds that we actually, I call, the soup of life, the components of life. Okay. Those you called amino acids, you mentioned those. That's very important, right? Amino acids. In DNA, we have cytosine, guanine, thymine, and adenine, right? These are the 4 nucleotides that are in DNA, basically. And so we look at all these double helixes and say, wow, they unzips and zips up like it does. Maybe that's why we're symmetric on both sides. We have bilateral symmetry. There's radial symmetry, probably supported by that, like we see in life forms, etc. Starfish, pentamerous, 5-side. So the thing is, Bennu, with these organic compounds, represents a satellite in our solar system of carbon-rich material that had an asteroid like that impacted the Earth in the past, would have delivered many, many carbon compounds to this planet, organic compounds, amino acids, as you pointed out. So this is why it's important to study these asteroids. Okay, now another thing about Bennu, if you look at the close-up images of Bennu, it looks like a rubble pile held together by mutual gravity. We don't know whether it's a rubble pile completely, but most likely, if it was going to collide with the Earth, and it's not, but if it was going to collide with the Earth, okay, and neither is Apophis, by the way, if it was going to collide with the Earth, it might be stretched and pulled by Earth's gravity when it got near, and the Earth's gravity might have pulled it apart if it was a rubble pile. Okay, so we would end up getting hit by strings of small objects that would burn up in the atmosphere. That's the best example, the best scenario. There might be a rocky core that collected all this material, and that rocky core might not melt. That might be the one that hits the Earth, but that might be much smaller than the 640 foot, or 1640 foot asteroid that is Bennu. So, it means a lot that we find these organic compounds out there, because the organic compounds are literally the primordial soup of life. And these are all the life-making compounds that are in the universe everywhere we look, it seems.
Yeah, because that's one random asteroid.
Yeah.
Particles are particles. They only combine so many different ways. To find proteins are complex. It's something that we have difficulty here creating and mapping proteins. That's a whole science in itself. But if it is just out there floating around here, then it's floating around everywhere in every galaxy that we just saw in that deep field image. And the idea of panspermia actually has a very solid ground, and that DNA seems to me, and RNA is universal. And when I say universal, I mean throughout the universe.
I totally agree with that, and interesting about Osiris Rex, the satellite that dropped that little probe and did that whole process. There was a woman who was a Catholic nun who was sitting in my dining room one time, and she was with another Catholic nun. This has relevance. And
where's this going? Okay,
I know.
Okay,
And as she sat there, she said, "I would love to see pictures the Hubble took." So I go down and I print out some photos in color for her to see. It's a small white-haired little old lady. So again, we talked about women in astronomy. Remember that? Okay, you talked about that. Relates to that. So I bring them up and I put them in front of her, and Sister Mary Ellen looks at them and says, "Oh, these are beautiful." And I start describing what she's seeing. Well, this is ionization of the hydrogen. Ionization, double ionization of the oxygen molecules make this beautiful teal color. Oh. And meanwhile, the other nun's laughing her butt off. I go, "What are you laughing for?" And she couldn't hold it more. She looks at me. She goes, "She's an astrophysicist." And I was blown away.
Right on.
And I was like, "Oh." And she was part of the not Osiris. She was part of the Near Earth Asteroid Rendezvous program.
Wow!
And worked with Goddard. She was at Goddard Space Flight Center, a little Catholic nun, unassuming lady.
Do you know who pulled Bennu off for us? Who got the most credit? Do you know this?
I don't. I'm
going to tell you right now.
Tell me then.
Brian May. Queen's guitar player.
Yes.
Queen's guitar player. Brian May, astrophysicist.
He's a great guy. Yeah. I know that. In fact, I wrote him once to ask him if he wanted to come on my live stream with the astronomy, but I never heard back who would write to me anyway, right? Because, but yeah, I like Brian May. He also did New Horizons. He did a song called New Horizons for the New Horizons probe to Pluto. Remember that?
Yep.
New Horizons. Yeah, I love that song. It was great. Really cool.
Smart guy, man. Smart guy. I remember when I was a kid, I've always been a huge Brian May fan. And if you're a guitar player, tone.
Mm-hmm.
Brian May is the cat. And so then I remember I was young and I was reading about Brian and maybe an interview, but all of my guitar playing and musician friends started talking about this. This is in the probably late 70s, early 80s. Dude, he's an astronomer. He wants to get a degree in astrophysics. He wants to go back to school. We all talked about it. Like, all right, cool, and sure enough, and then look what he ended up growing up and pulling off Bennu for us.
I know
it made the press somewhat. I think he downplayed it a little bit. He just did his thing, but it was a really big deal, man. Brian May.
Yeah. I mean, my favorite astronomer is Carl Sagan, and my favorite astrophysicist is Brian May.
Is that true? Is that true?
It's always been true. Yeah, Carl Sagan was my favorite. We are a pale blue dot, right?
Is it because Carl Sagan was a pothead?
It may be so, but I've never smoked pot in my life, which is probably not going to ruin me in front of your audience. Maybe, I don't know. But truth of the matter is, I always had medical issues as a kid, so I never did any of that stuff.
Yeah, I don't do that stuff anymore. It's been a couple of decades since
I
dipped my toe in it. Do you think Carl Sagan flip-flopped on the ET issue?
Yes, he did. He did a lot of that. And the thing is, and why wouldn't he? He was working at the university and trying to be, towing the university line. And when you're an astronomer, you can't come out and say, "I believe they're here." You can't come out and say that stuff. At least not then. Now you can. Did I ever tell you the story about when I was getting my degree? I actually, it became the title of my book. I told the guy that ran my observatory, the director of the observatory at the time, that I believe it's a populated universe. And he got kind of mad at me. Did I tell you that story?
Yeah, you did, but go ahead.
Okay, so I say to the guy, I walk in and I say, Art is a great guy. He passed, unfortunately. But I said to Art, I believe it's a populated universe, and he goes, and he had these glasses, he puts them over, big suspenders, big guy. He looks over his glasses like this, okay. And he goes, what is it, Mr. D'Antonio? Why do you insist on going down this path? Okay, like that. He's looking at me.
Yeah, right.
Well, here's what I think, Art. Okay, and I mentioned about the carbon fourth most abundant, etc. I said we're bilaterally symmetric. Okay, that's a very important development, and we're bipedal. Okay, and other creatures have radial symmetry. There's symmetry in every single life form. Art. He goes, and I said to him, and that's really important. And he's like, tell me why. Okay, and he's getting irritated with me, right? And I go, well, because this symmetry points out, okay, that when RNA duplicates and when you get that zip up of the second strand onto there, at the macro level, that creates this symmetry in all likelihood that we're seeing now. And I feel very strongly that this is something that occurs all over the universe. DNA is not just common to Earth. I think it's common everywhere. There's life forms of any kind. There's going to be DNA. And he looks at me and he goes, "Are you finished?" And I went, "Well,
Right.
Yeah." And he goes, "Get back in the observatory, get back in the project, and leave Captain Kirk to us." I was like, "Okay." And that was the last time I said it. And I said there were more planets out there, and he just like poo-poo. So in 1988, when the first planet was actually confirmed, I went back to the university. I graduated with a degree in 1983. So that's how old I am, see? And I went back in 88. I hadn't talked to him in 3 years. I walked in the door, smelled the old books in the library from the 1800s. Oh, the place just reeks of history. And I walked by the display cases with the old brass refractors. And then I walked into his office and the creaky wooden floors, walked to his door. He's on the phone bellowing about, I can hear him talking. I lean around the corner for the first time in 3 years. He hasn't seen me or talked to me. I lean around the corner with a smile, and he covers the phone. Remember the U-shaped scoop we used to talk to each other with, that famous telephone, the old phones? He covers the phone. And he goes, "It was only one planet." He actually, like, we never stopped communicating. It was like the conversation was continuing. And so I said, "Well, it's just the beginning, Art." And he goes, and waved me off. And I never talked to him again, actually. But we, of course, we're up to well over 5,500 known planets now around other stars. So, and that's just a small sampling, like you were talking about, that small size of the 3 moons in the sky. This is just a small sampling, fist size at arm's length over your head. In August is where this telescope was looking to see these.
Well, that reminds me of my. This is what I would ask ET, and it reminds me of the series 3-Body Problem, which is
great series.
Yeah, great series. Is that I would ask ET, how'd you do it? I wouldn't ask where are you from, interstellar travel, how you pulling this off, what do you guys eat for dinner, you guys like Van Halen. I'm not going to ask him any of that stuff. I'm going to ask, how did you do it? How did you evolve? How did you get to the point? Right? That's the lesson that we need. Yeah,
I agree with that. I mean, I've actually, another one of the talks I do is I talk about the evolution of life on other worlds. It's total speculation. But I talk about the very, very cool stars, the ones that are low temperature, of which there's more of those than any other kind in the entire universe. In fact, the very first star like that formed, they're called M stars. Very, very cool, low temperature. And they have the most planets of any other type, okay? And there's just more of those than any other type. So the first star that ever formed has yet to die in the universe. They last trillions of years. So they sit there. I call them the universe percolators. They just percolate and percolate and percolate like a pot that's boiling. They have low temperature. Any planets that form around them are very close to it. And because they're very close to the star in the habitable zone around the star, those planets are facing the star all the time, like the moon is facing the Earth. That's called tidal lock. And these tidally locked planets are very, very interesting worlds to me, because you can actually imagine offering trips to these M-star tidal locked worlds. You can go to a beach the whole day and night, the whole year. You can go to see sunsets all the time.
Where would
can
you
go.
build your house? Would you build your house half dark, half light
There you-
on the edge?
Yeah, so I could go to either or.
Yeah,
Yeah,
and go out the back door, go out the front door.
that's right. Go out the back door, go on the dark side. Go out the front door, go on the light. Hey, you
I
got
thought about
Travis.
that a lot. Well, look at if Alpha Centauri, right? And you
Yeah.
consider that, well, okay, it's in the right spot.
Yep.
But only if you live on that edge.
Yeah, that's right. And that's one of the big problems, okay, is these planets are so close to those M stars that the chances of them actually creating life that's maintained on that planet for billions of years, because they last trillions of years, they probably could develop life after the star reaches a phase where it's somewhat stable. These M stars are notorious for shooting off ultraviolet flares. They're called flare stars too. And so there's that problem. Now, we get ultraviolet flares from our sun too. We always have, but we don't have our atmosphere sterilized by it. Okay. They may, cause problems. So if there's an off chance, and there is, that some of these M stars are very calm, okay, relatively calm, or reach a point in their life where for a few billion years they're calm, then life could form, and maybe that'll happen. And I think that the likelihood is rather high that there will be life on one of these planets around the M stars in the habitable zone. And as you point out, you'd build your house on the terminator where you see perpetual sunsets. Now, the front side facing the star is always very hot because that's constantly heating, right? It never cools off at night. The dark side is always a little bit cooler because it never heats up. And now the hot air on this side will translate through that sunset zone to the dark side. And then you're going to get this situation where you have this wind blowing across your dark side, your light to dark side, the sunset side. And that wind could be devastating, could be massive, but it could still be habitable.
Here's the other thing. And with the 3-body problem is a decent example of this.
Yeah.
But our sun, we've had, 3 billion years, 4 billion years of low entropy, right? It's just kind of cruising along. Stable enough for us not to have burnt up. It fucked up Mars, but that's another story.
Yep.
But here on Earth, pretty stable. But once that hydrogen core burns out, our sun is going to go wacko. And when that happens, we cannot be here.
Correct.
There will be nobody on Earth to see that happen. We will have left by then.
Should have, yeah. When the hydrogen runs out on the Earth in the sun's core, then the sun's core is going to collapse because there's no outward pressure to keep that core going, keep the core up. Okay, the outward pressure is diminished, and the mass of all that sun is going to try and collapse it. So the core is going to collapse and get hotter as it does. And then it might start fusing helium into carbon. Again, there's that carbon again.
Well,
okay.
It takes 100 million degrees to do that. And
it's correct.
It may eventually get there.
Yeah.
And if it does, berserko happens.
Yeah. When that, as it collapses the core, okay, the sun actually gets hotter. And during that time, before the helium fuses to carbon, the sun is going to start to blow into this red giant. So long before any carbon is formed, this red giant from this outward pressure, this now hotter core, is going to push that out, the layers out. It's going to go beyond Mercury, possibly beyond Venus, and maybe envelop Earth. So it'll be inside the star.
It's going to take up the entire sky.
It's going to be a lot bigger in our sky.
It's going to be that big. It's going to be, and so as it's doing that over that period, which is a short period of time, it could be, some say 1 million years, some say 100,000 years, some say 1 billion years. Okay, that part doesn't matter what that transition is. What does matter is the temperature on Earth is going to go from this to a couple of thousand degrees very quickly. And so our atmosphere is going to burn away. The oceans are going to be gone. And so you can't live here. So we will have built starships, which goes back to my question to ET. How did you guys do it? How did you guys survive? Because we need, Mark, we have to live that long on this planet.
That's right.
We have to overcome disease, and we have to overcome an alien invasion. We have to overcome cosmic events, earthquakes, natural disasters, all of these things, nuclear war. We have to survive all of that to get to the point where we have to leave this planet. But if we don't survive all of those things, we'll never see the sun. And how many civilizations kill themselves off because of technology and never get to that point of an unstable star?
Sure, I think many of them do. Now we have 5 billion years left here, and we only need 1,000 years of that to get to the technology.
My guess, okay, this is my take. Forget physics. Forget all those PhD dudes.
Okay.
My prediction, after 5 billion years, that our hydrogen core is not what we think it is. I think we've got far less than 1 billion years before we switch to a helium core. And that's my take. I think our sun is, no, that's my take.
Okay.
There's
let's
no
say
way
you're right. Let's say you're right. Okay, let's run with that. Okay. We only have 1 billion years left.
Let's Brady Bunch this thing. Point at me again.
How much time, Jimmy, do we need to create a working starship or a working technology to get us off the planet? We just need about 1,000 years to develop a fusion reactor and this Randall-Sundrum 1 jump drive, we'll call it, punch in, punch out type thing. That's what we need, about 1,000 years. So in that billion-year time frame we have left, there's a lot of 1,000-year time frames in there. If we don't do it for the first 100 million years, okay, but that's a lot of time, right?
It is a lot of time. Well, okay, so before we run out of time, let's talk about time. What happens? Okay, this is my confusion with things. You watch Star Trek, you watch some science fiction thing, right?
Yeah.
And these ships are warp driving here and there, and they're dashing around the planet. What happens to time on those ships? They don't talk about that. You can't warp drive away from Earth and then come back and hang out with your kids. Your kids died 10,000 years before, even though you were gone for a few days. You can't warp drive like that. So if you jump into the 5th dimension and you ping it across to the other side of the universe and come back the same day, what happens to time here on Earth? If you're going to the other dimension, does Einstein not come into play and the speed of light?
No, speed of light is not a stopping point. You don't have a time dilation. That's the nice beauty of this. You don't have time dilation. You could go to Alpha Centauri and back.
You do it. You come back. I'm still here.
Yeah, if you started your show today at your time, 7 o'clock.
Mm-hmm.
Okay, I could go to Alpha Centauri in this technology, according to a Stanford physicist and a couple other people, in 20 minutes. I could go and come back before you went to your 5-minute commercial at the top of the hour.
And no time dilation.
No time dilation.
Interesting. So the twin paradox, all of that, it doesn't come into play.
Right. All that stuff only comes into play when you have to use equals mc squared. Well, the light speed derivative of that formula.
Yeah,
when you have to use
mass and velocity.
Yeah,
right.
You have to use the Planck constant and light speed. Yeah, that only comes into play when you actually have to travel within our 4 dimensions. If you can travel outside of our 4 dimensions, you don't need to worry about light speed, and you don't need to worry about those effects. So my beard won't be any longer. You won't be an old man going, "Well, it's about time he got back."
Right.
Who are you again? You don't have to worry about that. It's within our time frame. Now, there are things that happen in time that happen with time in that fifth dimension, but it's not a consequence to the fourth dimensional.
But what would happen? Okay, what would mess it up is if you did the fifth dimension, but you near a black hole, right? And then time, like what happened with Matthew McConaughey, right? When he went, what was that black hole called? What did they call that in Interstellar? It had a name, Gigantus or something.
Yeah, I don't remember.
But Kip Thorne, the problem with that was minutes to Matthew McConaughey was his daughter aged 80 years.
Yeah, I remember that. Yeah. Now, it's interesting. Yes, time dilation occurs. Again, that's fourth dimensional travel. Now, I sat with Kip Thorne for about 3 hours, and I talked to him about black holes. And we talked about, he talked to me about black holes. I wanted to hear what he said. And basically, he said, you could, if there was a such thing as a white hole where the energy comes out from a black hole going in, there's that concept of the white hole. I don't believe it, but neither does he really. But as a mental construct, he said there's a way that you can actually, as you're entering the black hole, you could see yourself coming out of the white hole before you actually go into the black hole, because the information comes to you. So in other words, that's kind of like a time dilation, time travel thing, okay, which is kind of interesting. You're seeing kind of the future before you get in, and it was like 3 hours of time, and I got what he was talking about. It was a long time ago, but he did talk about how he had an argument with Jimmy Hawking. Jimmy Hawking, that's you, Jimmy. And yeah, Jimmy Hawking, that's a good name for you. He had an argument with Stephen Hawking, and he basically said to Stephen that certain things can happen, moving toward a black hole. And Hawking said, no, that won't work. And they each rebutted each other. And Hawking said, oh, yeah, Kip, you're right. And then Kip Thorne said, oh, no, Stephen, you're right. So they swap positions. So even the smartest minds on the planet don't really have a solid understanding of the black hole and what it really means. Now, I'll tell you this, okay? You know how they say that it's an infinitely small point in the center, a singularity? Well, when we calculate gravity between the Earth and the moon, we calculate it as if it's at the center of the Earth and the center of the moon, okay? We don't calculate the whole ball and figure out some, integrated value. We can, and that's how we get the center point, right? The center of gravity. So that mass acts as if it's at the center. Same thing with a black hole. I don't know that there's any cosmologists out there that actually believe a black hole is an infinitely small point at the center, because we know a black hole around a galaxy in the Virgo constellation that's 5 times the size of our whole solar system. Mm-hmm. And it's the supermassive black hole at the center of Measure 87, a gigantic elliptical ball of stars, a galaxy. So if that can happen, there's got to be something in there. And as more mass enters it, it gets larger.
That's the only explanation for it. Kip Thorne and others, when they make these statements, they contradict themselves. Now, I'm thinking about this logically. Mm-hmm. I'm not a PhD, but if everything gets, anything that gets sucked into a black hole, that gets spaghettified and all of that, but that still has mass. Yeah. And then they turn around and say black holes have no mass. It's like, wait a minute. That doesn't make any sense unless everything is being ejected out, which we've seen some evidence of that, but we haven't seen a lot of it. The shape of a black hole is confusing. Is it flat? Is it two-dimensional? Is it spherical? Don't know. Kip Thorne represented the wormhole, by the way, in Interstellar as a sphere. And so we picture wormholes as, like an entrance to a cave, right? And then you just travel through. In Interstellar, if you remember, it was represented as a sphere, but black holes are not. What do you see with a black hole? Okay, so if you stay on the elliptical and you look at Sagittarius A, I'm just using our. I sound like an astronomer, huh? I
You're
sound
doing
like
good,
I know
man.
what.
I'm
Okay.
liking
So
this guy. This
so
guy is pretty smart over here.
yeah. So if you stay on the elliptical and you go to Sagittarius A, where we have a black hole, I still
Yes.
don't understand why we haven't imaged it yet. But that's another story. So
We have.
anyway, so that's no, not technically,
Oh,
but
we just see the stars orbiting it.
but is it flat? Is the black hole flat? If you're looking at it from the top, spiral galaxy, and you've got a black hole in the center. Here, I'm going to go to center screen. Spiral galaxy and black hole in the center. You're looking at it from the top. I understand that. Now, but you flip that to the side. Is the black hole of sphere, or is it flat?
Okay,
that's
I can
go ahead. Give me your best shot.
I can
Mr.
actually
Hawking.
clear up that confusion for you. Okay, if you look at a black hole, you got to remember that a black hole is distorting space-time. It's distorting space. Okay, so it's black holes all have these things called accretion disks. Disks of material that are going around them. Okay, like Saturn has icy little bodies going around it, right? But Saturn's gravity isn't nearly big enough to cause any distortion to the space around it. Black holes is. And now what happens is the accretion disk on the other side of the black hole is warped up like this. That is, the light is. The light is coming up and warping over the top and coming toward us. So it goes like this. So what do we see? From every direction we look at a black hole, we're going to see we'll either see a disk like this with a black hole in the middle, right? Or if it's at any angle to us like this, we're going to see a part of that far side accretion disk, where some of the light is going up, some of the light's going down, some of it's going out, but the part that's going up is going to be bent toward us. So that's why in the interstellar imagery of the black hole, for instance, you see the black hole in the middle, and you see a disk, and then you see a shadow, this bright thing over the top. That's because the accretion disk on the far side, the light is being bent. Now, light has no mass. So you might say, well, how come light can be bent if it has no mass? Gravity only acts on massive things. That is true. However, light follows the road of the universe, meaning light follows the curvature of space, like a car on a hill following all the bumps. Okay, it goes up, it goes down. Light does the same thing. If the universe is curved, light goes this way. Okay, if the universe is not curved, light goes straight or whatever. So a black hole, light comes up from that far side accretion disk around the other side of this black hole doing this, and it's trying to come up and go straight up, but the black hole is warping space and light's following it over the top and to us. So that's why we see the shape that we do. It's actually a physiological effect of gravity, powerful gravity, acting on a disk of light around the black hole.
But okay. So you're saying if you are suggesting that they are two-dimensional and flat.
No, the accretion disk has thickness to it. It's a disk, okay, but the black hole is
edge. It's on the edge. Okay, so the accretion disk is on the edge. If you're looking at the black hole from the front, and there's two, but there's one accretion disk that the light is swirling around this way.
Well, that's actually
another
matter.
one that's coming right, and there's another one in the front that comes around, and you see these animations, I should say, of black holes. And Kip Thorne always said that the black hole in Interstellar is the most accurate representation of a black hole.
Yeah.
And the way the accretion disk is represented there. But that's not what I'm talking about. I'm talking about the black part of the black hole.
Oh, that's a sphere.
Flat. Okay. See, that's what I'm saying. It's not from the front. Okay, so if I'm understanding you correctly, and now I don't know. I've thought about this a lot. I can go either way.
I have a model of it.
But if you take the galaxy and you flip it, the elliptic flat, okay?
Yeah.
Is there a black ball at the center.
Yes, there is.
We only see it represented as flat.
Yeah, okay. I don't know why you
follow
say.
it? You understand what I'm saying?
I know what you mean by flat. It's a sphere, but we can't see the roundness of it because of the fact that it's black. And when we say light, they say black holes are so powerful, light can't even escape it. What it really means is that space is so curved beyond a certain point called the event horizon, as you know, that light can't get away from the black hole. So it goes around and around and around inside the event horizon and never gets out. So we never could see anything coming out. Actually, if you were to disappear into a black hole just before you got, as you were getting spaghettified, okay, I would see you on the surface of that event horizon for a period of time, and it would just fade away slowly. Okay, because
that's correct. I understand that. Yeah.
Yeah, and the thing that's interesting is when you watch, when you look at a black hole, it's a sphere. I have a model in the other room. I wish I could get it, but it's a ball with a accretion disk around it, and you can tip up this backside. You can see what gravity does to the fabric of space around this black ball, and the other side of this is a single accretion disk. It's a single accretion disk. There's not two accretion disks. There's only one. But you're seeing an illusion because you're seeing the far side where its light is bent. So as the light leaves it, the light is bent over the top and comes to your eye. So that's light you see. You see light here, 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 and then you see the light here and here and here, and some of the light down here. So that is why you see a very complex looking black hole when you look at black holes in these photos. The Messier 87 black hole by the Event Horizon Telescope shows this exact issue, or shows this exact thing.
That's the only real photograph we have so far.
Yes, we're working on Sagittarius A. I've seen there's been preliminary data Event Horizon took of Sagittarius A, and that looks promising, and that's the closest one to us. But you have to remember something.
Why haven't we photographed a black hole that should be in Andromeda? And we have our galactic neighborhood right here. We've got galaxies all over the place.
Yeah.
You go down to Australia, you can see how many galaxies in the night sky in the southern hemisphere? 5, 6.
You got the Magellanic Clouds. Of course, you can still see Andromeda at times. There's a lot of other galaxies down there. I don't know the southern horizon, the southern hemisphere.
But my point,
I want to get a telescope in Australia.
Why aren't we photographing black holes all over the place?
Okay, it takes a special kind of telescope to do that. And the telescope we need is one that uses the whole diameter of the Earth in order to get the resolution required. Now, Messier 87, was it 44 million light years away? We're able to look at that one because it's massive. It's a gigantic black hole. As I said, 5 to 6 times the size of our whole solar system. So imaging that black hole was something within the limits, okay, that we had. So what happens is you have all these radio telescopes on the Earth, and the Earth's rotating, and as it does, you have this one telescope, and it images the black hole the whole time it's facing the black hole. Then this one does the same thing, images the black hole the whole time it's facing the black hole, and then this one does too, and they have it like 7 times. They combine all that together. It effectively makes an 8,000 mile diameter telescope. And that's huge. And they get a rough view of this black hole, and it takes lots and lots and lots and lots of compiling of data. They got to get timings right. They got to synchronize it all. It's very, very complex. But when they do, they get this image. But it takes a long time to actually come up with a good image of this black hole.
How many terabytes of data did they have?
Oh, I don't remember the number of terabytes.
I remember the documentary. I was like,
it
how much?
A ridiculous
petabytes?
Number.
Yeah, it was like crazy.
Petabytes or something.
Yeah, and it all had to be synced.
Yes, and it was just incredibly bad. And now the thing is, during the time that this is being imaged, well, material near the center of this black hole is moving very quickly. So it's conceivable that we could get some blurring by the material moving so fast. This is why, and plus it's a radio telescope, and plus it's not as high a resolution as a true 8,000 mile diameter telescope. Even so, we get a good representation of what the black hole should look like. Kip Thorne was right. All right, because what we imaged was exactly what he saw in Interstellar when you saw the data in Interstellar. And so the Event Horizon Telescope proved Einstein was right and proved Kip Thorne was right. And so this is, I think, a tremendous boon to astrophysics everywhere and cosmology, because now we actually see what a black hole looks like. And it is a sphere with one accretion disk, and the light is just bent over the top by the black hole's gravity.
How many different species are visiting this planet?
How many what?
How many different species are visiting this planet? We've got two ways to look at that: throughout history or today, right?
Let's do both.
Okay.
Yeah. All right. Here's the thing. In the Kimberley region of Australia, okay, we see the drawings in these caves of these creatures called the Wandjina. Okay, Wandjina were rumored to be travelers that came from the sky, lived under the water, and had full mastery of the water. They're represented as these oval-shaped heads with long, large black eyes. Sound familiar? And little tiny mouths. Okay, sometimes no mouth being shown, and they had halos on their heads. I did a whole talk on halos because I think the halo has turned up in all these different representations of deities around the world from cultures that never saw each other. But why a halo? I think it's something they saw and reproduced. That's another story. But anyway, so the Wandjina is one thing. Okay, in Val Camonica, Italy, there are warriors with helmets on. Okay, and these guys are represented as different creatures. Are they really warriors? Maybe. But think about this. I talked about our visibility to the universe. And I talked about the atoms are the same everywhere in the universe, right? So the technology will eventually be found by other civilizations in the universe. Maybe one civilization developed a triangular craft, which had a circular particle accelerator in it. Because again, that's probably the only way they can do it. Another technology came from a series of circular craft that they developed with particle accelerators. So another civilization might have orbs. Another civilization might have had these cigar-shaped crafts. Either way, I'm sure that there are several, I feel confident, there are several civilizations that are visiting us right now. Now, throughout history, I have a feeling that these same civilizations were probably just as advanced back then, because for what they're doing now required several, maybe 10,000 years of development, maybe longer, to get to the point they're at now. So they may have been as advanced, and maybe they have always been visiting us. You know,
that makes sense. That makes sense. My guess.
Yeah.
If I was going to Drake this thing, I would say the number is open. I think it could be infinite. I don't think it's dozens. I don't think it's dozens. I don't think it's hundreds. Nothing like that. No, I think it's a huge number, and I think that, Mark, for a couple of different reasons. Probably the majority of the intelligent species that visit this planet only do it once. There's too many planets out there to go and explore. So you're going to come by here, you're going to note it, you're going to give this planet a name, you're going to log it, and you're going to move on.
Yeah, it's possible.
That's what we're doing, right? So we're searching for exoplanets, and if we had a way to get there, we would, and go check things out. So how much of that is going on? There's a lot of life out there. So you're right. We have a beautiful blue gem here. So they're going to already know about us just from observing and looking for exoplanets. But how much comes here now? And then how many out of those, let's Drake equation this, visit a second time? How many hang out here? All right. So the number gets smaller and smaller and smaller. But I would say the visitation rate of different species, it's got to be an open-ended number. I would say it's in the thousands to tens of thousands if not per day, per year. That's why I know, we very rarely have the same experience explained or described. Yeah, we get the alien grays, we get that a lot, but look at us.
Yeah,
Look at us. Two arms, two legs, right? Stereo, everything.
Bilateral symmetry.
So why wouldn't ET look a lot like us?
That's the thing. They probably would if DNA was replicating the same way.
Exactly.
And so I don't find it odd that there's bipedal aliens.
I don't either. I
don't find it odd.
Surprised. Yeah. Right. I would be surprised if something shows up with 8 arms. That would surprise me. But
I don't believe an intelligent octopus is going to visit us anytime soon because, again, the pressures in an ocean environment are very different from the pressures on a land environment, so that they didn't go down that path. But you're right. I think that in terms of the numbers, the sheer numbers visiting us. Okay, Stephen Hawking also said we should keep ourselves down. So we just like
stay on the down low.
Down low. Don't become too noticed, right? So we're down here hiding.
Right.
Here we are. Okay, whoop, keep your head down, right? I mean, that's the kind of thing, right? That kind of crap. So, but unfortunately for Stephen Hawking in that regard, 2.5 billion years ago, we already started making oxygen in our atmosphere. Okay, phytoplankton and other, oxygen-making creatures that were on our planet were actually doing this. So our oxygen signal, the signal that says, hey, there's life here, guys. Hey, guys, everywhere over there, billions of light years away even, there's life here. All right. Now, but I'll tell you this, if they come here, even if for them it's not that big of a deal, it's a big enough deal, I think, that they would come here and stay for a while. And I think that they would probably still be here, and they probably start a chain of people, beings from these other worlds coming to study in an ongoing fashion. Because, in my view, if you get to the point where you're no longer worrying, you're no longer worried about disease, you're no longer, angry at your planetary leaders, okay, you're going to be scientists, and you're going to go exploring the universe for the sake of exploring the universe to find out what the universe is made of, the place in the universe. So maybe, just maybe, little tiny maybe, they're coming here because there's science teams wanting to learn about the life on this weird little world, And if that's the case, that explains a whole lot of other experiences. Like I had an implant shoved in my head that made me, it was so frightening. I had to move out of my old house, and because I couldn't stand to be there anymore. I had missing time as a kid that I could never explain, and after that missing time experience, I looked up in the sky a little afraid, saying, whoa, man, I feel like I got to look over my shoulder every time I'm out at night. Why? And then from that point forward, I said, I'm going to be an astronomer. I'm going to learn what's up there. I was 9 years old, Jimmy. And that was the defining moment, and then guys like Gentry Lee at JPL, sealed the deal with me and provided information and helped me to become an astronomer.
Is that right? I didn't know that.
Oh yeah. I wrote a space.
I'm a big fan of his.
Yeah, me too. Gentry Lee was named,
even though he ruined Arthur C. Clarke, though.
Oh, well, a little bit. Okay, we can forgive him.
He ruined Arthur
Forgive
C.
him.
Clarke.
Forgive that guy.
But no, he is just so smart.
He is.
And when I say he ruined Arthur had a way of writing that was dry with no human conversation. He couldn't do that. He had no way to it was emotional and stuff. Gentry comes along and added that element and the science part of it too as well. Yeah. But there was a change in the style of Arthur. I appreciated Gentry Lee. I've read all of his books. I'm a huge fan. But I like the old Arthur C. Clarke. Well, the childhoods and Arthur C. Clarke.
Yeah. When Bert Lee was just a scientist at NASA, he got a space station plan from a 10-year-old kid. That was me. And I wrote.
Is that right? Is that
yep,
right?
I made a space station plan on notebook paper because I was home for a month after surgery. I was 9.5. Okay. And I sent this thing to him. I had pigs and cows in the station, had these revolving dumbbells to make 1G of gravity, researched at the library. I figured out how to use carbon dioxide scrubbers with charcoal to take carbon dioxide out of the air. He loved that.
How old were you?
9.5.
Wow.
I was a dude. Look, I wear
pretty
glasses.
good. It's pretty
I have
good.
glasses. I'm a geek. Okay. Well, anyway, so I write this plan. I send it down to him, and I sit back and wait. Wait. 3 weeks went by, nothing. And then my mother says, "Mark, you got a box from NASA here." Whoa. I run up to this big box from NASA. I called it. I got my mother's magic marker and I wrote "space box" on all sides of it. I opened it up. Wow, there's a big folder with my space station plan. Threw that to the side because inside were models to build, books, kits, and other things, paper models, mission patches from the missions to that point. It was a box full of this stuff, and I just treasured that box. And then I opened up the manila envelope and pulled out my space station plan and a letter. It was a letter that said something along the lines of, "Dear Mark, your space station plan is incredible. We use a lot of the techniques you outlined in here. And if you read the plan, you'll see all my notes." What? And so I read the plan. Every page had Gentry Lee notes on it because the letter was signed.
Man.
The letter was signed Bert Lee, NASA.
Wow.
Yeah. And I actually talked to Gentry, a few years ago. It had to be like 45 plus years since I actually got that letter from him. And I wrote him and I said, "Hey, dear Gentry, you're not going to remember me, of course, but," and I explained this whole thing. And he wrote back a letter or an email to me within like half hour and said, "Oh my gosh, I don't remember that. You're right. But that's the kind of thing I did." Yeah. He's an amazing guy. So I was out at Alien Con and I was going to go to Pasadena to JPL and try and make an appointment with him, but I just didn't have any time. I had to do talks. I was there for A&E. They had me there because of Proof Is Out There, the show that I'm on, and so I really was there on their behalf. I couldn't really take time for myself, unfortunately, but I'm going to go back and I'll meet him, whether it's there or I probably he's retired by now. I don't know, but the bottom line is that sealed the deal for me. Okay. After the missing time event, I was always afraid to look up the sky. And then I felt I'm going to be an astronomer. And then I did that space station plan because I was thinking that way. And Gentry Lee just slammed the door shut on, "Yep, you're doing it." And I did it. He said, "Stay in the space program. I think you have a place there." I was like, wow.
Before we run out of time, I want to stay on Gentry Lee for a second and Arthur C. Clarke. We've only got a minute left.
Sure.
In the Rama series of books, right? Rendezvous with Rama, Rama Revisited, Rama, The Garden of Rama, and all of that. The ship, which is called Rama, was tracked for a couple of years on its way into our star system and was eventually going to arrive at Earth. And they had a date there. But that ship traveled fast, and it took like 2 years to slow down, right? And eventually, but it wasn't like a warp drive wormhole fifth dimension craft. This was a craft that approached the speed of light, didn't pass it, but was a traditional nuts and bolts craft.
Yeah.
What do you think about that approach? And could the James Webb theoretically pick up on something like that? Could we track something from deep space? And right now there's talk about something getting here in 2027. And I often wonder if it's like the Rama scenario presented by Arthur C. Clarke and Gentry Lee.
Interesting possibility. I think that concept you're talking about is like a generation ship. And at the halfway point in your journey, you got to turn around and start decelerating, to maintain that same amount of gravity, because you're accelerating all the way, turn around, we're 0G for a while, and then you start slowing down, and get your 0 G back, or get your gravity back again for your particular planet, whatever it is. So that has been an old standby, a classic, and it's the way that we were thinking of traveling if we're in our 4 dimensions. It's the only way we could do it in our 4 dimensions, is do that kind of thing. But it would be a generation ship. I mean, as it is, it would.
Well, that's what Rama was. It had cities in it. It was a long tube. I think, well, and if you go to like 3-body problem, that ET civilization was going to take 400 years to get here.
No,
you remember?
Yeah, I do. I don't remember the exact time frame, but I do know that in terms of the size of the universe, it could be anywhere from 8 years, okay, traveling under the speed of light, coming from say Alpha Centauri or Barnard Star or something, all the way up to thousands of years. If you're coming from some farther stars, it's unrealistic in our view, right, in astronomy, but it's not unrealistic in science fiction or my mind, that they could get here sooner than that from longer distances. Right. But with the 5th dimensional pop in, pop out travel, they thought they could do, they figured they could get to Alpha Centauri in 20 minutes, as I mentioned. Yeah, right. Using this. So if that's the case, that's 4.3 light years away. Well, they could go to, these other stars that are 6.8 light years away. Okay, 8 light years away. That's Sirius and its companion star. So there's Vega, 26 light years away. I mean, how long would those jumps take? It depends on how far into that 5th dimension they can go. And that means they have to build all these particles around the ship to actually move themselves into the 5th dimension farther and farther and farther. And it's more compressed. So that 1 foot, that theoretical foot I talked about, and of course they'd go like miles in there, that 1 foot would translate to a much greater distance the farther in you go. It's exponentially higher. So they could actually jump light years at a clip. And all they need to do it, by the way, all they need to make those particles would be a fusion reactor, like the one that Lawrence Livermore just had another success with. See, so things are connecting.
Marc, thank you so much, my friend. Where can everybody chase you down and follow your work?
Oh, you can chase me down at SkyTourLive.org. You can chase me down at fxmodels.com. I own a visual effects company, and that's our site. You can find me there as well.
Your YouTube channel is?
Yeah, YouTube channel is SkyTour LiveStream.
Okay,
and that's our observatories. We have these beautiful network of observatories. They're fantastic. We show you the universe live in real time, and it's really good. And we do it when the moon isn't full. So I mean, we have filters, but the moon being full, a lot of lights in the sky. So we like to show you faint things like galaxies and nebulae and stuff.
I love it, man. I love it, Marc. Man, just thank you for being a friend, and thank you for
so
all of the, no, I'm being serious, man. Our community owes you just a huge jumbo thank you.
Well,
and you know that we all love you, and just thank you for everything and your contributions to the world over the years. Just thank you so much. And it was great seeing you last week, and I can't wait to see you again, my friend. Thank you so much. Man.
See you soon. Bye, everybody.
Marc D'Antonio, everybody. Good night, Marc. Thank you so much. And with that, we're signing off for a couple of weeks. So everybody just be safe, have fun. I am heading out, and I will be back July 1st or 2nd, I think is whatever that Monday is, with Fade to Black. But I will be hanging out on social media and posting and live streaming and doing all kinds of fun stuff from around the world over the next couple of weeks. So until then, I want everybody to be safe, have fun, and I will speak to you when I get back. But for now, all I've got is go back, Lee Tappy. Fade to Black is produced by Hilton J. Palm, Renee Newman, and Michelle Freed. Special thanks to Bill, John, Dex, Jessica, Dennis, and Kevin. Webmaster is Drew the Geek. Music by Doug Aldrich. Intro, Space Boy. Fade to Black is produced by KJCR for the Game Changer Network. This broadcast is owned and copyrighted 2024 by Fade to Black and the Game Changer Network, Inc. It cannot be rebroadcast, downloaded, copied, or used anywhere in the known universe without written permission from Fade to Black or the Game Changer Network. I'm your host, Jimmy Church. Go back, Lee Tappy.